episode 10 of Breaking Down the Basics. This is a long form vid of discharge assessment. We're going to be talking about here, we'll show you some examples of some dispersion modeling like we talked about in the short form video. Also here in the long form video, I'll kind of break down the arrangement of a rupture disc and a PSV together, as well as when you should need containment or not. So in regards to the last thing I just mentioned, containment, we really want to look at with our occupational team and our environmental team, is this something we really don't want to release into the environment? And that's where we're looking at containment. Now, in this scenario, you may also need some overpressure protection on that containment device or tank. And so when you're doing that, what you want to do is you want to look at the relief conditions from your initial tank and your initial device, and then you want to calculate how big the containment needs to be to hold that expanded volume. Okay, so for instance, if you're talking about a fire case, now you're expanding the volume as that material is a hotter temperature. Obviously, you need enough containment for that expanded volume. Now, it's going to cool down and condense, but that's what we need in the original case. Sort of a good rule of thumb on that, too, is if you have a secondary containment that needs a pressure, you can set that second pressure relief device to about half of the initial. You're going to have some pressure drop into the containment, but that's kind of the overpressure rule of thumb there to help protect that second piece of equipment as well. You obviously don't want to lift two devices if you can help it in that scenario. The graphic then you're seeing right now is how we want to arrange a rupture disc and a PSV together. There's that pressure indication that we talked about in between. That's going to go off. You have a burst of the rupture disc. So this helps you in spurious failures where you don't just have a failure that you didn't know about, or you have a latent hole that is slowly leaking material out into the atmosphere. That interstitial space in there, then you're going to know if you have a leak into it, that you've got an issue and you can go out and check it. It also protects your relief device from seeing high temperature material or higher pressure material right below the lift point. That can corrode the device and make the device not work when it's intended to. So here we have a simplified P&ID or block flow diagram. What I've kind of depicted here on top of what's designated as tank 1 is the design that we were talking about earlier with a relief device and RD combo that has this pressure indication in between. What the pressure indication does is it acts as a tattletale or a telltale device and lets you know if you're leaking through this rupture disc. It's going to send an alarm and some sort of DCS or some kind of safety manager system to let you know that you are having issues with your rupture disc. The benefit there is you then don't have, whether that's vapor with entrained liquid or liquid itself, depending on the scenario, basically, coming in contact with that relief device all the time and potentially creating an issue with the relief device when you actually need it to work. Another thing we mentioned was dispersion analysis. Here's an example of a dispersion analysis case if you're wanting to evaluate the discharge of the PSVs and you want to know, is your community, is your personnel safe based on where we have this PSV routed. There's a bunch of different dispersion programs out there, like I mentioned earlier in this vid. This is just a low-high. It's a free version that's online. It has some limitations, but it's still used today for response personnel. As you can see, what you're looking at right now is just the site data and inputs that I put in. We're running an ammonia release. I put the location. We're going to run it in Beaumont, what time of day it is, what the atmospheric conditions are. There's some standard atmospheric conditions maybe that your company has or that you can find online. And then what's the strength of your release? Now, you're going to know that from a calculation of an actual release scenario, or you can, at face value, just use the capacity data for the PSV. Sometimes we do that, maybe not with the highest cases, but just the capacity of the valve that we actually have in there. That's a very conservative way to do it, but we know if it's good for the capacity case, and it's good for any case that we have. As you can see at the very bottom, these are the threat zone distances. This second graphic is actually showing you the dispersion based on an XY axis. Some of the other programs out there add in the Z-axis component, really give you some detail, a little more detail on this dispersion cloud. This is kind of, like I said, Aloha has a couple of limitations. One of them is that it runs it as a Gaussian model, which all of them do not. FAST is more detailed, kind of in between there is a safer trace model. But really, for your cases that's relieving toxics or flammables, this is a toxic release. You can run a flammable vapor cloud, LEL. You can run an impingement from a flame. This really is good data to tell you whether your PSV is discharging to a safe location and are you impacting anybody if you were to have a release. What we don't want is we don't want to prevent the equipment from rupturing, but then impact somebody by where we have this discharge going. So those are key things to think about whenever you're looking at the discharge assessment of your relief device. Hope you like the content. As always, you can check us out on YouTube, LinkedIn, Facebook, or at our website.